Let's take a look at another one. Here we again have a symmetric 3 by 3 matrix A. Because it is symmetric, we know it is orthogonally diagonalizable, which means there is some orthogonal matrix Q and some diagonal matrix D, so that Q transpose times A times Q equals D. Now, we saw this for regular diagonalization. We just saw it in the previous example. The entries of diagonal matrix D have to be eigenvalues of matrix A. The columns of matrix Q have to be eigenvectors of matrix A. So our first step is going to be to find eigenvalues and eigenvectors of A. Then we will have to take the additional step to make sure that Q is an orthogonal matrix, which could be a little bit more work, as we saw in the last example. So let's get matrix A into the calculator. We're going to let the calculator do the hard work and find our eigenvalues and eigenvectors for us. So A dot eigenvect gives me the eigenvalues and corresponding eigenvectors of matrix A. Okay. Now notice in this case we actually just have two eigenvalues. We have eigenvalue 3 and eigenvalue 6, but notice eigenvalue lambda equals 6 has a multiplicity of 2. So in the characteristic equation, there are two factors that would give us this eigenvalue. All right. And in this particular case, that means that we have an eigenspace for eigenvalue of 6 with a dimension of 2. If we want a basis for that eigenspace, we need two vectors. All right. So first off, the diagonal matrix is easy enough. I just need the eigenvalues of matrix A. Doesn't matter what order they're in. I could do 3, 6, 6, or 6, 3, 6, or 6, 6, 3. As long as all the eigenvalues are there, and in matrix Q, the corresponding columns of Q are eigenvectors of those same eigenvalues, we're good to go. I'll stick with 3, 6, 6. Okay. And of course, remember that for these entries that I'm leaving blank, they're just 0, right? We're just doing that to save some time. Okay, so I have my diagonal matrix D. Now, I know the columns of matrix Q are going to be eigenvectors of matrix A. What I need to make sure is that they are orthogonal to each other and normalized. So they need to be unit vectors and they need to be orthogonal to each other. All right. Now, when I have a symmetric matrix, vectors in different eigenspaces are guaranteed to be orthogonal to each other. So you could check this. 1, 1, 1 is orthogonal to each of these two basis vectors for eigenspace of lambda equals 6. Okay, if you take the dot product of 1, 1, 1 with either of these two vectors, you get 0, right? So they're orthogonal. But notice within an eigenspace, the vectors within an eigenspace don't have to be orthogonal to each other. So negative 1, 1, 0. I take the dot product of that with negative 1, 0, 1. I'm going to get positive 1, not 0. These two vectors are not orthogonal to each other. So step 1, I'm going to use the Gram-Schmidt process on any eigenspace that has more than one eigenvector as a basis, that has a dimension of larger than 1. Okay, to first find an orthogonal basis for the eigenspace. So for the lambda equals 3 eigenspace, we're good. We just have the one vector, right? That's fine as a basis. There's nothing else in that basis to be in that eigenspace to be orthogonal to. But for the eigenspace associated with lambda equals 6, since we have an eigenspace of dimension 2, we have two vectors. We need to use the Gram-Schmidt process to break down this into an orthogonal basis for the eigenspace. Okay, so for lambda equals 3, v1 equals 1, 1, 1 is beautiful. Okay, I will still have to normalize it, but it's going to be orthogonal to the other eigenspace because it's a totally different space. But for lambda equals 6, we're going to have to do a little bit more work. We're going to need the Gram-Schmidt process. So let's call v2 negative 1, 1, 0. And we'll call v3 negative 1, 0, 1. Okay? Remember, for the Gram-Schmidt process, get an orthogonal basis. The first vector just stays the same. I'm going to call f2. Let this be the first vector in my orthogonal basis for the eigenspace of lambda equals 6. Okay, so it's just going to be equal to v2, no change. But then, to get the next vector, I'm going to take the next vector in the basis I have and subtract the projection of this vector onto the basis, onto the vectors already in the orthogonal basis, which is, in this case, just this vector here. So I'm going to take v3 dot f2 over the norm of f2 squared times vector f2. Okay, that will give me a vector orthogonal to this vector that I already have. All right, so this one will require a little bit of calculation. Vector v3 is negative 1, 0, 1. v3 dot f2. So f2 is the same as v2, so I just need the dot product of this vector and this vector. If I multiply corresponding components, I'll get 1 plus 0 plus 0. So I'm just going to get 1 as the dot product. Okay, so the dot product is equal to 1. And in the denominator, I need the norm of f2 squared. So if I take the norm of this guy, that's 1 squared plus 1 squared plus 0. That's going to be 2. So square root of 2 squared is just 2. So I'm just going to get a half. Times vector f2, which is negative 1, 1, 0. And if I do the vector arithmetic, negative 1 plus 1/2 is negative 1/2. 0 minus 1/2 is negative 1/2. And 1 minus 0 is 1. This vector f3 is now orthogonal to vector f2. And these two vectors now form a basis for the same eigenspace that these vectors form. So these are now orthogonal to each other. Okay, and so they form an orthogonal basis. All right. So now we have 3 vectors, 3 eigenvectors that are orthogonal. But we want an orthogonal matrix, which means we need the columns of the matrix to be orthonormal, not just orthogonal. So they need to be unit vectors. All right, so now I want to take each of these vectors, this vector from the lambda equals 3 eigenspace, and these 2 vectors forming a basis for the lambda equals 6 eigenspace. I want to normalize all these vectors. Okay, so I'll call my normalized vector for the lambda equals 3 eigenspace, I'll call it u1. So I'm going to normalize it just by taking the original vector v1 and dividing by its norm. That will change its length to a unit length. Okay, so I get 1, 1, 1. And the norm of v1, 1 squared plus 1 squared plus 1 squared is 3, so I get square root of 3. So I get 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Okay, so that's going to be one of the columns in my orthogonal matrix Q. Now I need to find the other two columns. I know these vectors are orthogonal to each other now. Now I need to normalize them so they'll be orthonormal to each other. Okay, so let's call U2 the normalization of F2. So -1, 1, 0 is vector F2, and the norm of vector F2 is -1 squared plus 1 squared plus 0. That's square root of 2. So I get -1 over square root of 2, 1 over square root of 2, 0. That's going to be another vector or another column in the orthogonal matrix Q. Finally, U3, I'm going to take vector F3 and I'm going to normalize it. So F3 over norm of F3. Vector F3 is -1/2, -1/2, 1. The norm of that, real quick, -1/2 squared is 1/4, plus -1/2 squared, that's another 1/4, so that's 2/4. And then 1 is 4/4, right? So it's going to be square root of 6/4 once I add it all together, or that reduces square root of 3/2. Okay? So if we do the vector arithmetic, if I take -1/2 and I divide by the square root of 3/2, and I fully simplify, I get square root of 2/3. Okay, and maybe I'll just show you exactly what I'm doing there because it is a little more complicated. I'm dividing by a fraction, albeit in a square root, but it's still a fraction, so I can multiply by the reciprocal. Okay, the key here that I'm observing is I've got a 2 down here, and I've got a square root of 2 up here. 2 is just equal to the square root of 2 squared. So I could cancel this square root of 2 with one of these square roots of 2. Okay? And I'm glad I'm doing this because I realized I made a mistake here. That would give me 1 square root of 2 down here with a square root of 3. I'm going to get square root of 6 in the denominator. I wrote square root of 2/3, and that's not quite right. It'd be -1 over square root of 6. Okay, this is exactly the same. -1/2 divided by root 3 over 2. I'm going to get -1 over square root of 6. And finally, 1 over square root of 3 over 2. I get square root of 2 over 3. Okay? Okay. What we have now is not just an orthogonal basis, but an orthonormal basis for the eigenspace. Okay? So we're still in the lambda equals 6 eigenspace, but now these two vectors are orthogonal to each other. That was through the Gram-Schmidt process right here. And then we normalize them right here. So now these are orthonormal to each other. They form an orthonormal basis. And they're going to also be orthonormal to this other vector in a different eigenspace because it is in a different eigenspace. For distinct eigenspaces of a symmetric matrix, the vectors in different eigenspaces will always be orthogonal to each other. Okay, if it's not a symmetric matrix, the different eigenspaces do not have to be orthogonal to each other. But for a symmetric matrix, they are. So we've done all the hard work. Let's construct matrix Q. Okay, this is going to be our orthogonal matrix. Now, our eigenvalues are in the order 3, 6, 6. So the first column of matrix Q has to be an eigenvector, and normalize a unit eigenvector of eigenvalue 3. And then the second and third columns of matrix Q will have to be orthonormal eigenvectors from the lambda equals 6 eigenspace, a basis from that eigenspace. All right, so lambda equals 3, we already found this guy, we've normalized it. 1 over root 3, 1 over root 3, 1 over root 3. That's going to be my first column for matrix Q. Okay. The second column of Q is going to be one of the eigenvectors from the lambda equals 6 eigenspace. So I'm going to use these two vectors because they're normalized, so they're unit vectors, and I've made sure they're orthogonal to each other through the Gram-Schmidt process. Okay, so the first vector, it actually doesn't matter. I can use this vector next or this vector next because they're both eigenvectors of lambda equals 6. Okay. So let's use this one next. Negative 1 over root 2, 1 over root 2, 0. Negative 1 over root 2, 1 over root 2, 0. And finally, this is my last eigenvector. It's also an eigenvector of lambda equals 6. Negative 1 over root 6, negative 1 over root 6, root 2 over 3. Okay. And we're done. We have a diagonal matrix D and an orthogonal matrix Q, so that Q transpose times the original matrix A times Q is equal to the diagonal matrix D. And Q is an orthogonal matrix. Each row of Q is orthonormal to every other row. Each column of Q is going to be orthonormal to every other column. And you can check if you take Q transpose times Q, you're going to get the identity matrix.